Hello everyone. In this video, I'm going to discuss the solutions and initial value problems, which is a second section here after the first video. So if you have an int order ODE, right? So if you have some int order ODE, then usually it is kind of relating independent variable to the nth derivative, right? And usually the lower order derivatives as well are involved in it. And let's give you just an example using a second one so we make sure we don't confuse the order with the other exponents. So if you have x squared times the second derivative of y with respect to x plus x times the first derivative here plus y equal x cubed. So definitely here, this is a second order and x, the independent is x and the dependent is y. So let's write this example. 1 minus, and you have in parentheses inside the second derivative, dt square minus y equals 0. So here, this square root here may confuse you because it looks, we're used to like if you have some square root or something in square and things happen. But here the derivative is second order, right? So that doesn't change. Order is 2. The independent variable is t, and the dependent variable is y. Okay. So the nth, let's say n equal 4, which means the fourth derivative here equal to xt. So you have the order is 4 and the independent variable is t and the dependent is x. So in general, we can say that these equations fall under this format in general, some type of function that is relating x and y and derivatives of the independent with variable with respect to or the dependent variable with respect to the independent variable. So this is just kind of a notation that speaks in general, or a kind of a general form, where f is a function that depends on x, y, right? And the derivatives of y up to whatever order we have, let's say n here. So we're going to assume that the equation holds for all x, of course, and some type of interval. So it needs to hold for all x on some type of interval. So we can, of course, rewrite this, and that's one of the goal here in the course, is to rewrite the highest order derivative in this format. So the highest order derivative, to rewrite it as some function of x, y, and the derivatives that are left there. What's going to come next? All right, so if this is the highest n, then what do you think next? It's going to be n minus 1. Okay. So which is often the best form or preferred form for the computational purposes, especially in the applications. So let's talk about a good definition, which going to be here called explicit solution. So if you have a function, all right, phi of x that when substituted for y in equation, then when substituted for y in, let's tell you, of course, this equation, whichever, but let's start with this one here. This one, let's call it star. When substituted in star, and of course, or 2, that's, or this one, that's also included, or that or that, they're equivalent. Satisfies the equation for all x in interval I is called explicit solution. So if you have some function and you substitute it for y in this equation, and it satisfies the equation, of course, for all x, on whatever interval we're looking at, I is called explicit. Then is explicit solution. And most of times solution are write it this way. All right. So the idea here is simple. Instead y, you're going to put this phi of x. And if it satisfies the equation, then it is an explicit solution. And of course, if the derivatives are involved, then you're going to calculate the derivatives. So let's do some examples on this. Let's say that we have this function we want to try. And see if it is an explicit solution to this. So linear equation. Let's try that first. So what does this mean? It means I have the second derivative involved. So I will need to calculate the first one and the second one. All right, so power function here, 2x times 1 minus -1 times x to -1 minus 1, -2. All right, then second derivative, which is the one that we have here. It's going to be derivative of x is 1, then -2 again, x to -2 minus 1 will be -3. So 2 minus 2 times x to -cube. And let's see if this works. So this is the second one, which is here, minus I'll put it there. Then minus 2 over x squared, which is this part, times y, which is now this. That we're testing, right? So what we're actually doing, before I do it, so you see, instead y, this is what we're trying to figure out. Okay, so, and now we have everything that we need, and you can go ahead and try it and see, and you can pause the video and see. So this leads to 2 minus 2x to -3 here, minus 2 over x squared, x squared minus 1. All right. Yeah, it looks like 2 when you distribute these cancel, the negative times negative is positive. Then these two -1, this goes up, becomes -2. All right, so we get 2 minus 2x to -3 minus 2 plus 2 times x to -3, which is 0 because these all cancel. So yes, this function that was proposed is a solution to this, or explicit solution to this differential, to this linear differential equation. All right. So you should try this one. Pause the video and try it for this function x cubed, and you should find that it's no. Okay, next thing is to check or to show that any choice of this C1, C2 constants will allow this function to still be an explicit solution. So let's show you. So you have a function that involves, and these actually are prep examples that will help you when you actually find solutions and you understand how they work, because now we're doing kind of the backward. You're testing it, just like if somebody says x plus 1 equal 3, and says x is 2, and you plug in 2 and you say 2 plus 1 equal 3, that works. So kind of same idea here. So let's say, and it also allows you to see these nice properties with this type of functions. So here we're going to try to show whether these constant C1 and C2, do they matter or change this function and not make it explicit solution, right? And the linear equation to this kind of linear equation here, all right? So pause the video and think about the first step. Or if you want to test whether this function is an explicit solution, what would you do? Oh, okay. All right, so this is what we're doing. You have your background, you can do your derivatives, and we plug them in and then see what happens and whether these constants dictate something or not. All right, so I think I'll, for the time here, I'll try to give you. Of course, the derivative of the EX is going to be the derivative of this power here times that function. So, so when you do here, right, that's going to give you this negative. And this one, the derivative of 2x is going to be a 2. Um, keep going. Same thing again. And we get 4 C2 E2 EX. All right, so now I just need to put everything in one equation, which is, oh, this is freezing. Let's see, freezing is, come on. I think I'll try go to next. Freezes here. The cold weather is affecting it. All right, so you know the next step here. You just need to put everything that you have in the equation. And of course, if let's say we factor this e to negative x, you'll get c1 plus c2 minus 2. And if you factor, no, c1 plus c1. So c1, these factor, we get these. Then this and this and this, we need to get these. This minus 2 c2 minus 2 c2. Yeah, which is 0. All right, so this holds for all x, which means these constants c1 and c2, it doesn't matter what they are going to end up making this function that is c1 e to negative x plus c2 e to 2x to be explicit solution to the linear differential equation that is given. Okay. So last example here, of course, it's nice to have this explicit, but not all the time they are explicit. So let's see that, let's do an example here where to show that this y squared minus x cubed plus 8 equals 0 implicitly defines a solution. This is implicitly defines a solution to this equation. And on some interval, of course. Let's see. So one way to do this, there are different ways to do, but I think since it's implicit, let's take y squared and solve it for the others here. So it's going to be x cubed minus 8. So that means when you go from y squared to y, you need to do plus or minus square root of x cubed minus 8. So here we have 2 to try, but I think if we try 1, it's going to give the other. So here, this implicit form, let's call this function here, take the first one. And of course, we know how to do the derivative of this. The first one, you're going to change, of course, this to x cubed minus 8 to 1/2. And the derivative will be 1/2 times the inside derivative, which is 3x squared, times that x cubed minus 8, 1/2 minus 1, which is negative 1/2. I'm sure you've done this so many times in the past. Right, so we can write it as 3x squared, and 2 is here, and square root of x cubed minus 8. So that's this first derivative. Okay. So if we take dy dx equal 3x squared over 2y, all right, so here dx here equal 3x squared over 2. You see this part is actually the phi here, right? Which means, of course, dy dx equal 3x squared over 2y. So because of the this here a note, you have for the derivative, the first derivative, you have x cubed minus 8 for real numbers. It equals to 0 here when x, let's say, equal 2. But we don't want for the first derivative to be 0 because it's in the denominator. So x cannot be, and I'll give you some more details. And of course, for this to be defined, then x has to be greater than 2. So that makes the interval 2 to infinity, excluding infinity, because you want that interval to be defined. So if x, let's say 0, you get a square root of negative 8, which is undefined. So for us, so two things are involved here. It's the denominator and it's the square root that gives us the interval. And we can do the same thing for the other negative square root, right, of x cubed minus 8. And we'll find that it's also an explicit solution.